Hi, today I'm going to show a demo on how to run 3D graphics applications in RacEr GPU. So yeah, actually we have a lot of requests coming from a lot of customers and from research community how to run any graphics animation or make a movie on RacEr GPU. So today I'm going to discuss on that. So before that, show a real demo on that part. I'd just like to walk you through how to use our RacEr GPU or any of our products. As you may know that our products are deployed in a cloud. So in order to access that, you have to register in AWS on the top right here. So go to this link and then register yourself, and then in the AWS Marketplace, and then you select FPGA developer AMI, and then you select after that you select F1 2x large. Then you have to do a lot of configurations for uh, memory and use the TCP/IP protocol and what else? Yeah, so most of the part that's it. And then you launch the instance. So and then it will ask you to connect the instance using SSH or PuTTY. That you have to connect. You need to have a key. So if you don't have a key, it will you can create a key there, and then once you have the key, then you can connect SSH or PuTTY. So assuming that you have a FPGA image and programming models, so that today's demo focused on that part. So as you know that our products can support C, C++, Fortran, Python, PyTorch, CUDA, or you name any applications, x86 or x64 application, it can support. So that's because we have our own compiler called Vivid compiler. So Vivid compiler is a C, C++ Fortran compiler which can do a lot of things in a native POSIT format. So the flow chart is shown on the left side here. Okay, so in order to do that that part, what you have to do is okay. So let me so yeah, in order to have graphics computing applications, so you need to use a Blender. So Blender is open source. I would say software. So you can download it from blender.org, and then you have a Linux version here download. So you just click on the download here, you have Linux version. But my most favorite one is this one. I'll go to this wiki blender.org, and then what we did was that we downloaded from the what we did was we took it from the source. What we did was that in that case we have the source code, and then we did it from the source itself. So but one difference is that so since it uses the x86 or x64 CPU, so in our case, since we are using our uh, RacEr GPU. So RacEr GPU is I would say it's a 412 core CPU in a 2D mesh network. You can see on the left side here. So they are connected in 2D mesh network with on the PCI slot, and then DDR memory is there. So on the right side you can see that the two-dimensional 2D mesh network in a grid. So each core is it has its own identity in a three-dimensional space. So as you can see on the box, for example, 200 in the sense it's on the second row and the zeroth column and zeroth space. So the grid network is it's connected. So in order to access the CPU, you need to have this identity. So yeah, as you know that a lot of graphics application, for example, I'll show you where the render application is used. Okay, so render used in a lot of promotions, as you can see in the architectures, building architectures, or industrial automation, or movies. So it used in a lot of platforms for visualization. So in order to use this the render, it requires a huge computing power. So what we did was that we tweak the code of Blender. So wherever the compute intensive things are there, so we have partition the code in a such a way that so each CPU assigned to a specific task, specific computation. So we took the complete source code, repartitioned the code, and then rebuilt from the source as given in this link. So just go to just follow this instruction, and then yeah, so uh, and then you can build from source. Just you need to have this make file. Just in order to build, you need to have a you need to build from yeah. So you need to just enter make, yeah, so that it will build from the source. Okay, once it builds from the source, and then it is the binary stored in this in directory blender hyphen git build underscore linux bin. It's there. Okay, so in a lot of the graphics computing, it uses a lot of trigonometry functions, addition, multiplier, square roots, and so forth. Square roots or inverse square roots are used in a lot of lighting applications and movements and so forth. As you can see in the bottom slide here, this is one equation. It's one of the things. For example, this is used. This equation is frequently used in the vehicle drift, wherever it is moving on the curve. So this kind of equations are used. As you know that this is very compute intensive. So yeah, so we have to partition code in a such a way that we can increase the frames per second. So next, what I will do is I will show you how to use this software in a virtual desktop, or I would say remote desktop, and then I will walk you through how to invoke this Blender, and then I'll show which demo I used to make a to run a benchmark on it. Oh, at the AWS console here. So what you have to do is in order to invoke that part, so you have to have a virtual desktop machine. So in order to have the virtual desktop, what you have to do is that you have to create a port, virtual port, TCP/IP port, in order to invoke that virtual desktop. Since the instance is running, so before launching instance, so what you have to do is that you have to come down to the security groups here, uh, and then click on the inbound rules, and then edit here. Then you have to add custom TCP/IP rule here. So 8443 and for all. Then click save. Since I already added, so I'm going to just cancel it. Once you have this part, um, then what we have to do is that, so go to the console. Then we have written a shell script in order to connect a desktop here. So here the desktop connect connect. Okay, connect.sh. So then you have to enter new password and so forth. After that, so since I already connected the desktop, I'm not going to enter any new password here. So okay, in order to connect to uh, the virtual desktop, you need to have a nice DCV. This one. Uh, this you can download from nice DCV downloader here. okay, for Windows x86-64. So then once you have that, so what you have to do is come down to the instances and then click on the public IP here. So just copy this public IP, and then since we open the port, so just click on 8443, enter 8443 and then ask to connect. Okay, then you have to enter the username you created. So this username is created in the shell script, and then the password you created in the shell script. Okay, now it's authenticating. Now it's connected to virtual desktop. Okay, now what you have to do is click right, then open terminal. Okay, so once in the terminal, what you have to do is you have to invoke a Blender. So in order to invoke Blender, go to this directory, Blender -git build underscore Linux bin, and then there is a Blender binary. So just execute this command /Blender. Then you get interface like this. Okay, so we are using this promotional video. So it's about it's a about 10-minute video. So what we did was that in this software, so we have created a promotional video for this vehicle. Then we benchmark it for GPU, CPU, and our RacEr GPU. So note that we are not going to show how to create a promotional video here. So you can find this kind of videos or tutorials online. So you can go to it and yourself. But the purpose of this video is to show how to run any graphics computing applications, RacEr GPU. And then I'm going to compare with this promotional video with CPU, GPU card, and with our RacEr in terms of frame per second. Okay, so what we did was that we ran that vehicle modeling or promotional video for about 5 minutes in different platforms, CPU, GPU, and in our RacEr. So with 1080 pixel, so in HD format. So as you can see, the peak performance in different hardware. So in CPU, peak performance was about 74.3 frame per second. So that is due to as a render designed for the CPU, and a lot of codes are executed still in a sequential manner, and it is still using a floating point arithmetic. So that's why you see very less frame per second. Similarly for GPU, you can see that frame per second was about 117. Well, GPU meant for accelerating graphics computing application or scientific computing application, or you name anything which math, GPU are the best one. But still, in case of peak performance, it's not so high, because they are using a floating point arithmetic and a lot of the memory bottleneck. Last one you can see in the benchmark is that RacEr GPU. So in terms of peak performance for a wide full HD for 108 pixel, The frame per second was about 212 frame per second. Uh, so that is due to, you might be wondering why it is so high. That is because we partition the code, Blender code, in a such a way that wherever it is compute intensive, we directed those codes to RacEr GPU, and moreover, so our products such as RacEr GPU based on POSIT number system, so it requires half the data width compared to the floating point. So you can see there is a speed in arithmetic computation, and not only the speed. So since it's computing fast and there's not so much memory bottleneck, you can that's why you can expect the better frame per second. So since the data is reduced by half, you can see that the memory consumption is going to be reduced by half. So that is why in most cases in you can see a lot of graphics computing application or scientific computing applications or any applications which has POSIT based, it has a lighter memory overhead. Okay, so yeah, that's it. So if you have any questions, please do get back to me or send us an email, and I will be more than happy to clarify your concerns. Thank you.